Have you ever wondered what space-time is? This question has intrigued many great minds throughout history, and it's one that takes us on a journey to the very fabric of the universe. Space-time, in its essence, is a conceptual model that marries the three dimensions of space, length, width, and height, with the fourth dimension, time. Imagine a cosmic loom, weaving together the threads of space and time into a single unified fabric. This is the tapestry of the universe, and it's a key component of our current understanding of physical theories. These theories tackle some of the most profound questions we can ask. How do relativistic effects come into play when we approach the speed of light? How do massive objects like galaxies or even black holes move within the universe? These are the puzzles that the concept of space-time helps us to piece together. The architect of this groundbreaking concept was none other than Albert Einstein. Prior to Einstein, scientists had separate theories to explain different physical phenomena, but Einstein, with his pioneering spirit and a mind that dared to think differently, saw a connection. He envisioned a framework where space and time were not independent, but interwoven. Einstein's theory of relativity, which proposed this revolutionary idea, didn't just change the way we perceive space and time. It fundamentally changed our understanding of the universe and our place within it. It's a testament to the power of human curiosity and the relentless pursuit of knowledge. But as with any scientific concept, our understanding of space-time is ever evolving. It's a complex and fascinating journey that has seen contributions from other brilliant minds, each adding their own threads to the fabric of space-time. From Newton's laws of physics and Maxwell's electromagnetic models to Minkowski's space-time, each has played a part in shaping our comprehension of the cosmos. So, are you ready? Let's dive into the fascinating journey of how our understanding of space-time has evolved. How did we come to this understanding of space-time, you might ask? Well, our journey begins with two separate theories that existed before Einstein's groundbreaking work. First, we had Isaac Newton's laws of physics. These laws described the motion of massive objects. They explained why apples fall from trees and why the planets orbit the sun. Newton's laws provided a framework that could predict the motion of objects under a wide range of conditions. But Newton's laws couldn't explain everything. Enter James Clerk Maxwell and his electromagnetic models. Maxwell's theories explained the properties of light. They told us why light behaves the way it does and why it travels at the speed it does. Now, these two theories, Newton's laws of physics and Maxwell's electromagnetic models, worked perfectly well in their own domains. But there was a problem. They didn't play nicely together. They were like two pieces of a puzzle that just didn't fit. At the end of the 19th century, a series of experiments were conducted that revealed something special about light. Measurements showed that light always traveled at the same speed, no matter what. This was a bit of a head-scratcher. Why would light behave this way? In 1898, the French physicist and mathematician Henri Poincaré speculated that the velocity of light might be an unsurpassable limit. Around the same time, other researchers were considering the possibility that objects changed in size and mass, depending on their speed. These ideas were like sparks in the dark, lighting the way towards a new understanding of the universe. They challenged the existing theories and hinted at something deeper, something more profound. These experiments were the stepping stones to a groundbreaking theory, and so the stage was set for a new player to enter the scene, a physicist by the name of Albert Einstein. He would take these separate theories and disparate ideas and weave them together into a new theory that would revolutionize our understanding of the universe. But that's a story for the next scene. In 1905, Einstein presented a theory that changed our understanding of the universe. This was the birth of special relativity, a theory that shook the foundations of physics and set the stage for a new understanding of space and time. Imagine a world where the speed of light is the ultimate speed limit, an unbreakable barrier that governs the entire cosmos. This is precisely what Einstein proposed. He suggested that the speed of light was not just fast, it was constant. It didn't matter if you were standing still or hurtling through space at breakneck speeds. To you, light would always appear to travel at the same speed. This was a radical departure from the traditional view. To accommodate this constant speed of light, Einstein had to rethink our understanding of space and time. He proposed that they were not separate entities but aspects of a single unified framework, space-time. But here's the twist. Space-time isn't the same for everyone. It's relative. It changes depending on how fast you're moving. If you're in a super fast rocket, time would appear to slow down, and lengths would appear to shrink compared to someone traveling at slower speeds. It's not that time and space are playing tricks on you, they are genuinely different for you because of your speed. This is the essence of relativity. But why would space and time conspire to keep the speed of light constant for all observers? It's a mystery that has captivated physicists for over a century. One thing is certain, this bizarre behavior of space-time is fundamentally tied to the nature of light. Einstein's theory was a game changer, but he wasn't alone in this intellectual journey. His ideas built upon the work of many others, and they were further developed and refined by those who came after him. In the next scene, we'll explore one such figure. Hermann Minkowski, the mathematician who gave us the concept of Minkowski spacetime. But that's a story for another moment on our cosmic clock. Enter Hermann Minkowski, the mathematician who gave us the term spacetime. A German scholar, Minkowski delivered a groundbreaking idea in a colloquium back in 1908. He stated, "Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." This bold announcement marked the birth of what we now refer to as Minkowski spacetime. But what does this really mean? Well, in simple terms, Minkowski proposed that space and time are not separate entities, but rather they are interconnected parts of the same fabric, which we call spacetime. Minkowski's concept of spacetime wasn't just a philosophical musing, it had practical implications in the world of physics. His spacetime model serves as the backdrop of calculations in both relativity and quantum field theory, two pillars of modern physics. Relativity, both special and general as proposed by Einstein, deals with the large-scale structure of the universe. It explains the motion of planets, the bending of light around massive objects, and the passage of time in the presence of gravity. Quantum field theory, on the other hand, deals with the smallest particles in the universe. It describes how particles like electrons, photons, and quarks behave and interact with each other. In both of these theories, Minkowski's space-time model plays a crucial role. It provides a framework within which these vastly different scales, the incredibly large and the incredibly small, can be understood and connected. But Minkowski's spacetime isn't just about linking the large and the small, it's also about understanding the nature of reality itself. By merging space and time into a single entity, Minkowski challenged our everyday perception of the universe. He presented a vision of the cosmos where space and time are intertwined, where the events that occur are not just located in space, but also in time. Minkowski's work helped solidify the concept of space-time, but there was more to come. Einstein wasn't done yet. He had more to contribute to our understanding of space-time. After his groundbreaking work on special relativity, Einstein set his sights on a new frontier, gravity. He proposed a radical idea that would forever change our understanding of the universe, his theory of general relativity. In this theory, Einstein envisioned space-time as a fabric that could be warped and bent by mass and energy. Much like how a heavy ball placed on a trampoline stretches the fabric and causes it to sag, massive objects like planets and stars create distortions in the fabric of space-time. And it's these distortions, these curves in space-time, that we perceive as gravity. To put this into perspective, imagine a marble rolling along the surface of the trampoline. It would naturally follow the curve created by the heavy ball, spiraling inward. This is akin to how the Earth orbits the Sun, not because it is being pulled by the Sun's gravity, but because it is moving along the curves in space-time created by the Sun's massive presence. Our understanding of this was further solidified by a NASA mission called Gravity Probe B. Launched in 2004, this mission set out to measure the shape of the space-time vortex around Earth. Its findings, revealed in 2011, closely accorded with Einstein's predictions, providing strong evidence that our planet does indeed warp the space-time around it. So in essence, when we speak of gravity, we're talking about the twists, turns, and curves in the fabric of space-time. We're talking about the dance of celestial bodies along the contours of this cosmic fabric, a dance choreographed by the mass and energy of the universe itself. While our understanding of space-time has evolved tremendously, it remains a complex concept that continues to fascinate scientists and curious minds alike. So next time when you drop an object and it falls to the ground, remember, it's not just falling, it's following the curves in the fabric of space-time.